Good morning, everyone. Today's lecture will be on examining the exponential response in greater detail. And after that, we will start looking at more generic solutions to both RL and RC natural response problems. So if you recall from our discussion last class, we were looking at the way in which, if you give some energy to any of the energy storage elements. I think in the last class we looked at only the inductors, but today we'll also look at the capacitors. And you have a resistor or some bunch of resistors in the path. Now we saw that once you remove the excitation, or in other words, if you remove the independent voltage source or current source, which was providing energy to your energy storage element, and you just disconnect the source, we saw that the energy dissipates over a period of time, right? We saw that the current through the inductor has a general form, which is something like this: e to I naught e to the power of minus t by tau, right? Where tau we said was equal to L divided by R, correct? So here what we are seeing is, now today we are going to look at this property. What is this e to the power of minus t? Okay. So if you plot it in the time domain, that is to say the x-axis is time, okay, and y-axis is, let's say, I of t. So the analogous form would be applicable to both the to RCs for in the case of RCs it will be the voltage, right? Okay. So here, let's say it is starting at a point I naught, right? And then we know the shape, right? Like all of us know the shape. It is kind of coming something like this. Okay. Now first, at t equal to 0, we know that I of t is I naught. This is trivial. Okay. Now when does I of t reach 0? Okay. Let's say this is case 1. Okay. When does I of t reach 0? When does it reach 0?
T is equal to infinity.
T equal to infinity. So from the mathematics we know that as t tends to infinity, I of t reaches 0. Okay. Now suppose you want, you're waiting for this. Okay, as of now we only saw about how it decays, right? Let's say you have to measure the time when the current kind of comes down to an acceptable value which is close to 0. Okay, so here we saw, suppose you are waiting for the current to drop down to 0 before you do something else. Okay, we will see that when you have a forced function, you will also see that how it exponentially goes up. All right, and so there also it has the same behavior. Okay, let's say you have a capacitor or an inductor and you are waiting for it to charge down completely. Now our mathematics is telling us that the inductor's current will completely come down to 0 only if you wait for an infinite amount of time. Okay. Now let's say you want to do a lot of other things. Okay. Let's say after the current comes down to 0, you want to switch on something else and then do a lot of other work, and you cannot wait till infinity. Okay. Now what can we do? Our mathematics is telling only at t equal to infinity, that is, we wait for a very, very long time. Okay, that is when it drops down to 0. Mathematically, absolute 0 will happen at t equal to infinity. But as you can see here, the current keeps dropping down to smaller and smaller and smaller values as the time goes on. But absolute 0 will happen at t equal to infinity, which is, let's say, for all practical purposes, non-existent. Okay. Now you might have started off with some amperes of current. It might come down to nanoamps, come down to picoamps, come down to femtoamps, attoamps, and even further down. Okay. Now where do we draw the line? Okay. if somebody is going to come and ask you, hey, how long will this circuit take to discharge? Okay, can you say t equal to infinity? No,
No,
you
sir.
have to give some time, right? And we also saw that as tau changes, let's say if this L and R combination, this L combination and R combination changes, let's say there is another tau 2, okay, tau 2 equal to some L2 by R2, totally different values. And let's say this is tau 1, and if we say tau 1 is lesser than tau 2, how do you think the response would be?
The first one would decay.
The decay will be less in the second case.
The decay will be less in the second case. That is to say, it will take a longer time. Okay, I should not draw a straight line here, but okay, something like this. Okay, so here tau 2 is greater than tau 1, right? This is making sense. So there is some dependence on this tau, correct? Now, so if somebody comes to you and asks,
Yes, sir.
how long will this circuit take to discharge? We have to come up with some metrics. Okay. Now, how do we come up with these metrics? Let's try to find out what happens, what exactly happens with this tau. Okay. So let's say I of t by I naught is given by e to the power of minus t by tau. Correct. Let's see what is the fraction. Okay, when t equal to tau. When t equal to tau, let's say I of t equal to tau by I naught, what will be the ratio?
1
Can
by
you quickly calculate?
1 by
That will be 1 by e. Can you tell me in percentage?
0.36.
63%.
Yes.
Okay, 0.36, okay, or 36.79%.
Yes.
Okay. Now, when t equal to 2 tau, okay, I of t equal to tau by I naught, what will happen? It will be 1 by e squared, right? What is the value in percentage?
13.5.
Sorry?
13.5.
13.5%. Okay. When t equal to 3 tau,
4.9%.
4.9%. Okay. When t equal to, let's say, 4 tau, let's also do up to 5 tau. Okay.
1.8%.
1.8%.
1.8%.
0.673%.
0.6.
Okay. Now, what are we basically saying here? If we kind of redraw this, let's okay. Let's say this is tau, this is 2 tau, 3 tau, 4 tau, and 5 tau. Okay, something like this. This is the time. Let's say your time constant, if it is 1 millisecond, you're talking about 1 millisecond, 2 millisecond, 3 millisecond, 4 millisecond, and 5 millisecond. And if this is I of t rationalized to I naught, okay, at t equal to tau, you have dropped down by a factor of how much? You have, if this is 1, okay, let me, I of t by I naught, okay, this is 1, okay. By the time you wait for one time constant, it has come down to 0.367 or 36%. By the time you wait for two time constants, it is not a linear response, it has come down to 13.5%. Okay, and for three time constants, how much it is? It is 4.9% of the initial value, right? And then what happens at 4 tau? It is 1.8%. 5 tau, it becomes 0.67%. Okay, so typically sometimes, you might, depending on your application, you might say, hey, okay, I am more bothered about, when I'm able to reach within 5%. Okay. Let's say I want to reach within 5% of the initial value. This is my settling tolerance, right? Then what happens? You say that you have to wait for how much time here?
3 tau.
Approximately 3 tau. Now somebody might come and say, no, I want 1% settling. Okay. You can call it 1% settling. That is like, I want to see that I would consider my system to have settled if the final value reaches within 1% of the, if the value of the signal reaches within 1% of the final value. Okay. Then how much time should we wait for?
So 4.6. So 4.6.
Correct. Yeah, if you back calculate, okay, if you say I of t by I naught is 0.01 is equal to e power minus t by tau, okay, you will end up with t equal to 4.6 tau. Okay, all right. So some people might say 10% settling also. All right. So depending on your application, but typically people say, okay, 5% settling means wait for 3 tau. 1% settling means wait for 5 tau, or approximately 5 tau, okay, or 4.6 tau to be very accurate. All right. So this is what this is the behavior of an exponential system. Okay. Although theoretically or mathematically the signal will asymptotically reach the final value. Asymptotically means that it will never reach the final value, but it will only get closer and closer and closer. And it's only at t equal to infinity we say that mathematically it reaches the actual final value. But in any practical system, that is the notion of waiting for an infinite amount of time is absolutely pointless. Okay. So we need to come up with some metrics. And typically when people say, okay, I need 1% settling, you say, okay, wait for 5 tau. If you say 5% settling, you say, okay, wait for 3 tau. All right. And so on. Okay. Another interesting thing that we can learn from this is basically, if you see I of t equal to I naught e to the power of minus t by tau, okay, for if you, let's say if you differentiate it with respect to time, okay, d by dt of I of t, that is basically the slope of I of t. We know that it is coming down. What can you say about the slope? Let me.
It should tend to 0.
Correct. So if this is the, okay, so where is the slope the maximum?
At I naught.
At I naught. Okay, at t very close to 0, this is where you have the highest slope. Okay, and as you go ahead in time, the slope starts decreasing, right? And then finally, as you pointed out, the slope goes down to tends to 0 as you go to t equal to infinity. So with this understanding, if you look at this differential, what do you get? You will get minus I naught divided by tau e to the power of minus t by tau, right? So now if you were to evaluate this this is the differential, right? And if you were to evaluate it at t equal to 0, okay, now what happens? The slope becomes
Minus I
Minus I naught by tau.
correct. Sorry.
Yes, sir, it's all right.
Yes.
This is
Yeah. So the slope becomes minus I naught by tau, or if you take the rational I naught by I by I naught, it becomes 1 by tau, and basically the slope here will meet, if the slope is like this, it will cut the x-axis at tau. Okay. So this is the way in which your slope will behave. Okay. So any doubts, any questions? Okay. All right. So have you studied the exponential response even earlier? You have, maybe in school or something?
Yes, sir.
Yes, sir.
Okay. Okay. Then maybe I need not have spent so much time, but it's okay. All right. So let's do one. It's okay. So now let's look at. I think we had looked at RL circuits last time. Okay. Now, if you have RC circuits, how do we do? You have R, you have C. Okay. Now, if you write a mesh equation, let's say this is VR and let's say this is VC. Okay. So what do we say? VR plus VC equals 0, right? And we can say that VC plus C times D VC by dt is 0. Now we can move things around. dVC by dVC by VC equal to minus V by RC. Sorry, minus dt by RC, right? So you can integrate it, and what will you basically get? You'll again get I mean, here both the voltages are the same, and so you will basically get natural logarithm of V equal to minus T by RC plus K. Now you can substitute for the initial condition, right? And you will basically get the same kind of expression. V of T will be some V naught e to the power of minus T by RC. All right.
Sir,
So we looked at RL circuits where I was the one which was current was the exponentially decaying function, right? Here we have the voltage which is exponentially decaying, because the voltage in a capacitor, across a capacitor, cannot instantaneously change, right? Okay. So
Sir, like VR minus VC, right? Because of the polarity.
yeah, if you correct, VR minus VC, but then how are we getting the current flow to happen? Okay, so if you okay, yeah, you're right. VR minus VC, then probably we should have the okay. The current is flowing like this. Yes, you're right. But the current direction is in which direction? Let's say this is charging out. Okay, so the current is going to go like this. All right. Uh, just a minute. Okay, basically the current direction is like this. Okay, and we are okay, if you go around like this, VC minus, okay, it's basically a
sir,
subtraction. Yeah, sorry, this you'll have C into R also. Okay, I didn't
sir,
go through this. Yeah,
if we write the expression Q equal to CV
Yes, sir.
and then we take dq by dt, actually that dq by dt,
Sir, this expression
so
is
sir,
Sir,
that dq by dt, uh, actually that will be negative, and as we
correct,
have considered IC and we have taken the direction, so IC equal to minus dq by dt, and then the expression will come correct.
correct. Yeah, you're right. You're right. Correct,
yes, sir.
because the rate of change of current is negative, right?
So
So
initially we assume some charge capital Q on the capacitor, and then after some instant we say Q minus
yeah,
small q,
correct.
and so dq by dt comes out to be negative.
Yeah, you're right. So basically, finally, you end up with this equation. Okay. So you have the same exponential behavior, right? And you will, yeah, you'll basically end up with the same exponential behavior. Okay. Now let's try to solve a problem. Okay, I'll just go through it because I mean, even in the book it was something like this. I don't know what I'm missing out here. Okay. Um,
So I have a doubt.
I think okay. You can probably yeah. Tell me your doubt.
Not here in the last slide, sir.
Okay.
So here you said that if we like extrapolate the tangent at I naught,
Mm.
uh, then we get at the time axis. It cuts it at tau time,
Yeah.
like time tau.
Yeah.
So I've even seen this in class 12 textbooks. We were also taught this,
Mm.
but I never knew the significance of this. It only says that okay, if the decay is according to the initial rate, then it
Mm.
will take only tau time to
Correct.
fully uh, so the current to become zero. But what
Correct.
it what's its significance to say this, what's its application or something like
So one basically that is not going to happen. Okay, and if you are looking at the rate of change of current or voltage at that the time which is close to t equal to 0, okay, if because in some cases you might be interested in how much current is getting or so in this case the current is decaying, okay. So whereas if you want to know the rate of decay or the correspondingly if you want to look at the inductor voltage, it will be L di by dt, right? If you want to know what will be the voltage across the inductor when this is happening, so that is where you might look at the equivalent thing in capacitors. So when a capacitor is charging, okay, or if it is discharging, okay, you will basically need to know how much current is being drawn, okay. So that is kind of the you will see that this capacitor charging discharging happens in these switching circuits, okay, any switching circuits or for that matter any of these digital logic circuits, okay. So when the capacitor is switching, okay, when let's say the capacitor is charging or discharging, the current waveform will kind of look something like this. Let's say it will have a current like this, okay, and then things like this, okay. So let's suppose you have an inverter and it is connected to the supply. The supply current will look like this, okay. The polarity is in the opposite direction because like for a voltage supply, current flowing out is taken as negative, right? Flowing in is taken as positive. So if you are interested in what will be this kind of peak currents that you are getting, okay, then this will be of some interest, okay. But yeah, cutting the x-axis at tau, basically, it's just a mathematical exercise. You don't have much significance. But if you are looking at the rate of change, and with that, if you are calculating, let's say, the voltage across an inductor or the current which is flowing through a capacitor, okay, then this slope will make some sense, okay.
that? Okay, sir.
So
Thank you.
faster switching circuits will have more peaks or larger peaks, okay. Slightly larger time constant circuits will have lesser peaks. That's if you want to look at the current waveform when it is charging, or equivalently the voltage waveform when it is when you're looking at an inductor. This makes sense, okay. All right, so let's try to solve some problems in capacitors, okay. So there is this, let's try to solve this. Let's say we have 80 ohms here, okay, and we have a capacitor 2 microfarad, and we have 70 ohm, and we have a 50 volt source, okay, and let me right. So initially the switch is connected like this, okay, and the switch moves in this direction at t equal to 0. All right. Now the question is, what is V of t, or the V of t as defined here? Let's say what is V of t at t equal to 0 and t equal to 160 microseconds.
Sir, at V of 0 it will be 0,
Right.
and then at 160 seconds it will be 1 minus 1 by E into 50, sir.
You can calculate and tell the value.
Okay, sir.
Okay. So V of t, this will be 0 here and here. So what is the tau? The tau that we saw here is 1 RC, right? Tau that we saw is 1 by RC. Okay. I don't know if I mentioned it here.
RC,
Okay. So
RC.
sorry here. So tau here is becomes 1 by RC. Okay.
Shouldn't it be RC
Sorry, I'm
only?
sorry. Tau is RC. Tau is RC. Okay. And you can use, so it becomes e power t minus t by RC. Minus t by RC. Okay. Yes. So our V of t at t equal to 160 microseconds is around 18.39 volts. Okay.
Sir, at t is equal to 0, the capacitor is fully charged. We can assume that, right? That is, it has a potential of 50 volts across it.
Yes. 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 It's been connected for a long time.
Sir, VT we have to find across the resistor or the capacitor.
It will be the okay at yeah, actually the question was across the capacitor, but I just made it across the resistor. Let's find out across the capacitor. Yes, sorry, across the resistor. Yeah. Okay, so let's
Which one, sir?
move to the next one. All right. So now in some of the circuits that we have seen till now, okay, what we have seen is basically that we had either one resistor or one capacitor. I mean, you can either have one resistor, one capacitor, or one resistor, one inductor. I think some of the problems that we did earlier, we had like one resistor, multiple resistors, but that can be kind of collapsed down to a single resistor. Okay. So now let's say if there are multiple resistors and energy storage elements. Okay, I'm just making it general. When I say energy storage element, this can be either C or it can be inductor. All right. Now what you can do is first form the equivalent. Oops. Okay. First thing is you can form the equivalent energies, either equivalent C or equivalent L. Okay. So sometime using parallel series, combinations. First find out the equivalent amount of inductor or the equivalent capacitor. Okay, reduce it down to one capacitor or one inductor. Secondly, sometimes it might be very easy to find out the resistance seen from the by the energy storage element. Okay. Now, sometimes if you have, let's say, some resistors, one resistor, and then you have, something like this, and then you have an inductor, it is fairly straightforward to find out what is the resistance which is seen by the inductor. All right. But sometimes it may not be very straightforward. Okay. So in those cases where it is not very straightforward, especially if you have a dependent current source or a dependent voltage source, okay, then what you need to do is you need to find the Thevenin equivalent resistance Thevenin equivalent resistance seen by the either L or C. Okay. Now that you have this, you can form the you can calculate the time constant tau, which can be given as L equivalent divided by R equivalent, or tau becomes 1 by R equivalent or into C equivalent. Okay, and then you can solve for the systems. Okay, because many of these systems will not exactly have one single resistor or one single inductor. Many of the problems will have multiple inductors and multiple resistors. Okay, so in those cases, this is the way that we solve the problem. All right. Now there is one more thing that I want you to understand.
Sir, it is RC, right? Tau equals to
1 by RC. Oh, I'm sorry. I keep writing. Yeah, I'm sorry. Yeah.
So what do you mean by forming an equivalent capacity C or equivalent L circuit?
Yeah, we will work out some problems. You'll get it clear. Okay. So let's say you have 2-3 inductors in the circuit. Like you can combine those inductors to get an equivalent inductance. Okay. We'll work out problems. Then these doubts will get cleared. Okay. All right. So before we just jump into the problem, just want you to understand one thing. So, there is this concept called as, 0 minus and 0 plus. Okay. Now, you might say, what is 0 minus 0 plus? That doesn't make mathematical sense. All right. Now, basically, its definition is, okay, a limit of some value, let's say the current or the voltage, either voltage across the component or current through the component, when t tends to 0 from the left side. What is the left side? That is from minus infinity onwards as you come towards t equal to 0. Okay, where t equal to 0 is the some switching happens. Okay, at t equal to 0, some switching happens, right? So when you approach 0 from the left hand side, what is the value that you get? So that is what is called as, let's say, V of t is 0 minus or I of 0 minus. Okay, so V of 0 minus or I of 0 minus. All right. Same way, 0 plus is basically nothing but limit of t tending to 0 from the right hand side. Okay, what is right side? As you are coming from t equal to infinity and you are going towards 0 from the right hand side, what is the value of, let's say, V of 0 plus of 0, V of 0 minus? Okay. Now still it might be a little mystery to many people, many of you. Let me clarify a little further. Okay. Now for an inductor, let's say some switching has happened. All right. For an inductor, okay, when some switching has happened at t equal to 0, what can you say about the current I of 0 minus and I of 0 plus?
they'll be same.
It will be the same. Why will it be the same? Because an inductor cannot change the current through it instantaneously. Okay, so current through an inductor cannot change instantaneously. Right? So I of 0 minus and I of 0 plus will be equal. Okay, the voltages can change. All right, but okay, the current does not immediately change, but maybe because of the external factors, some voltage might change, but then the current does not change. Okay. Now, at t equal to 0, your v of t also will not change. For a capacitor, okay, what happens to a capacitor? The voltage across a capacitor cannot change instantaneously. Correct. So voltage across a cap cannot change instantaneously. Right. Okay. Now, of course, the current through a capacitor can change, okay, but the voltage cannot instantaneously change. Now, what happens is for a resistor, what can you say for a resistor? Let's say there is a V of 0 minus and V of 0 plus. Okay. Of course, in a resistor, both follow. What can we say about this?
Are equal.
Nothing.
Sorry? Yeah, it need not be equal to. Okay. It need not be equal to. Because our resistor can change the current and the voltage, the voltage across it and the current through it instantaneously. Okay. It can change instantaneously, and so there is no necessity that before switching and after switching, at the very instant of switching, okay, when we are talking about 0 minus 0 plus, we are basically just artificially kind of dividing the time, okay, and then saying that instantaneous change. Okay, in practice, instantaneously maybe nothing changes, but then when you're just slicing at 0, okay, when you have a step function, okay, when you just remove the connection, that instant when the switch is opened or the instant when the switch is closed, okay, this is what we are talking about. Okay, all right, so let's solve some problems, then it will make a lot of sense. All right.
Sir?
Yeah.
Sir, when you have no resistance in series with the capacitor, then it will change instantaneously, right?
Okay, so what happens is that is more of a mathematical problem which does not exist in practice. All right, so basically what you're asking, is like this: you have a battery and you have a switch, right, and you have a capacitor, right? Let's say you're saying at t equal, this is basically what you're asking, right? Okay, so this is a mathematical problem. Okay, so you can kind of break your head over what can happen at this instant of time. So because we are talking about all ideal elements, then we say this will happen when I of t will become infinite. Okay, at t equal to 0. You understood? Because this is a pure mathematical problem. Yes, in practice, what will happen? Any battery or any voltage source will have some R. Okay, this is the VSRS. The switch will have some resistance, R switch. Okay, and then you'll have the capacitor. Okay, so basically now you have a time constant of tau equal to RS plus RSW into C. Okay, so this is what happens in all digital circuits. Okay. If you have an inverter, AND gate, any gate that you take, basically you have capacitors charging and discharging, and they are getting charged and discharged through the switch, where you have a MOS switch. In most of the, all modern ICs are out of CMOS. So the MOSFET will act as a switch, and the MOSFET will have some switch resistance. Okay, and this is how it works. All right. But the first case which you said, where the voltage source is ideal, capacitor is ideal, and the switch is ideal. So when you talk about a pure ideal mathematical world, you also get some unreasonably ideal values like I of t becomes infinite at t equal to 0, and that's why instantaneously it will change. Okay.
So,
yeah.
so can you please go to the previous problem?
Yeah.
Yeah, in this, the voltage across the resistor at t equals to 0, why did we write 0? Because when we switch, then shouldn't it get the same voltage as across the capacitor?
Yes.
Yes. Yes, it will. Okay,
So
so okay, maybe now with this understanding, we should say, okay, let's say t less than 0 or t equal to 0 minus. Okay,
Okay, sir. Thank
okay,
you.
that's the thing. Right. So let's solve this problem. I think we'll get little clarity after we start solving problems. Okay. So we have an 18-volt source. We have a switch which opens at t equal to 0. And then we have a 90 ohm resistor. We have a 1 millihenry inductor, 50 ohm. We have a 2 millihenry inductor. Someone had a question about what do you mean by equivalent inductor. We will understand it through this problem. Oops. What is this? Okay, so oops, there is one more resistor. All right, so this is the problem. I1 is defined as the current which is flowing through this resistor, and I2, where is, sorry, IL is the current which is flowing here. Okay, and the question is determine I1 and IL. Okay, so basically you should say what will be the value of I1 and IL before t equal to 0 and after t equal to 0. Okay, so I think just a minute before you start solving. Basically what I said was the procedure is first you form the equivalent inductor or equivalent capacitor, then find out what is the resistance which is seen, find out the tau, and then for all the currents and voltages, okay, wherever applicable, okay, there will be some initial condition. Okay, so for example, if at t equal to 0, if something is switching, okay, you need to write it as I of 0 plus e power minus t by tau. Okay, or v of t can be written as v of 0 plus e power minus t by tau. Okay, now this initial condition depends on which particular current or voltage that you are looking at. Okay, so just keep that in mind, and as we solve this problem, it will become abundantly clear. Okay, so first let's find out what is the L equivalent here. We have three inductors, right? What is the equivalent inductance?
2.2 millihenry.
2.2 millihenry. Okay, you
11 by
have 2 and 11 by 5 millihenry. Okay, you have 2 and 3 in parallel and then 1, so it is basically 2.2 millihenry inductor, right? Now the same, I mean, why this IL current is flowing through this inductor and it gets split to two different inductors. Okay, so anyway, the parallel combination, the equivalent inductance combination takes care for all these effects. So this is our L equivalent. Okay, now if this is our L equivalent, what will be our R equivalent? So we can kind of redraw the circuit and like you have a 2.2 millihenry inductor and you have some 50 ohm, right? And you have some 90 ohm. And once you remove the source after, so this is the circuit after t greater than 0, right? So you have 60 plus 120, it becomes 180 ohms, correct? This is how the circuit looks like t greater than 0, because the exponential decay and everything happens only after t greater than 0. So you have 180 ohms, 90 ohms and 50 ohms. Okay, now you can find out what is the equivalent R, what is the R equivalent here?
1110.
It is yeah, you're right,
110.
it is 110 ohm. Okay, very good. So this is our L equivalent, this is our R equivalent. So what is our tau? that is L equivalent by R equivalent, which becomes
Sir, I have a doubt.
yeah.
1 by
Sir,
5
why didn't we short the source?
We are not shorting the voltage source. We are opening it, making it an open circuit.
But when we take like Thevenin equivalent, we like short it, right?
No, as I
Short the
mentioned,
voltage
first of all, this is the circuit after t equal to 0. Okay, after t equal to 0, the voltage source does not come into the picture at all. Okay, before t equal to 0, it is a steady state condition, and therefore there is no basically there is no transient which is happening there. All right, but after t equal to 0, that is where the transient response comes. Okay, transient meaning that is where this e power minus t by tau type response comes, and in that case the voltage source is not at all in the picture. Okay, that's why I specifically mentioned this is the equivalent circuit after t equal to 0. Is this making sense?
Yes, sir.
Yeah. Okay, someone has written 0.2 into 10 raised to minus 5. Okay, so that is the tau. Yeah, 2 or 20 microseconds, or this is the thing. Okay, we are running out of time. So what I would do is I would ask you to solve it. I'll just basically tell you the way it should be. I1 can be written as I1 of 0 plus e power minus t by tau, and IL should be written as IL of 0 plus e power minus t by tau. And the thing is I1 0 plus is not equal to I1 of 0 minus, because it is a resistor current, whereas IL of 0 plus is equal to IL of 0 minus. So use this, solve the problem. We'll continue in tomorrow's class. Okay. So any doubts, any questions? Okay, all right. So have a nice day, everyone. Thank you. Okay, there was some confusion today about how this, how we derive the RC response. So I made a small mistake. I'm just correcting it now. So if you have an R and a C circuit, R and a C connected like this, okay, and let's say the current flow is something like this. All right. Now we are assuming at t equal to 0 minus, okay, the value V of capacitor voltage is some V naught. Okay. Now at t equal to 0, the circuit is as shown. Okay. So basically there was something which was charging the capacitor, and now we have removed that source or whatever was charging the capacitor. Now what will happen? So basically we the equation that I wrote was correct. It was a nodal analysis. By mistake I told that it is a mesh analysis. So basically at this particular node, what is the current which is flowing? The sum of currents is 0. So if it is V by R plus C dV by dt equal to 0, where V is basically the voltage across both resistor and the capacitor. Okay, because both are in shunt. Okay, I mean you can think of it as shunt, series, whatever, but at the end of the day the voltage is basically the same. All right, now here we can rearrange terms, okay, and say that dV by V, okay, can be written as minus dt by RC. All we are doing is basically moving things around, and you get basically that dV by dt, so is equal to dV by V is equal to minus dt by RC. Now if you take the natural, if you integrate, you get natural logarithm of V e power minus sorry, here you get basically minus t by RC plus some integration constant k. And what happens is we will substitute the initial condition at t equal to 0 or 0 minus, okay, or 0 minus or 0 plus. For the sake of capacitor, for the capacitor it really doesn't make any difference. Okay, V of 0 is V naught. right? So if we substitute that, k becomes natural logarithm of v naught. Okay. Now what happens is we can rearrange things to write natural logarithm of v by v naught is equal to minus t by rc. You take exponential on both sides, you get v is equal to v naught into e power minus t by rc, and this gives rise to the time constant is equal to rc. Okay, so we basically do nodal analysis here and we end up with the same result. So this is just for clarification. Thank you.